Bismillahirrahmanirrahim. Dear students, the title of this video lecture is Structure Factor. This is an important factor or quantity in crystallography that tells you about the intensity of the scattered beam of the crystal lattice. This is denoted by FHKL in the subscript, and this FHKL in the subscript equals this equation. This is sigma I from 1 up to n, and this is f of I exponent 2 pi I hui plus kvj plus lw. This is basically I, right? So you should make this correction. Sorry for this mistake. This is hui plus kvi plus lwi. So it means that hu, like hkl and uvw, both the directions and hkl planes are important. So where does it stem from? This question is very important. Basically, when a beam of electron or X-rays or neutron impinges upon a crystal lattice, then not all crystallographic planes take part in the diffraction. You remember this. Some of the planes take part in diffraction, and they re-radiate, the intensity and hence the beam. So in some directions we obtain some intensity, right? And this scattered intensity depends upon the position of atoms and hence crystal structure. That is unit cell of the crystal lattice. For example, if we consider a simple cubic structure, then the scattered intensity of this sort of lattice will be totally different from the one whose crystal structure is body-centered cubic structure, right? And this body-centered cubic structure will give you intensity totally different from the face-centered cubic structure. So it means that this structure factor depends upon the atomic arrangements, as I told you, and this is UVW. These are the coordinates, and this influences the intensity of the scattered beam. And also it tells us which reflections, that is peaks, HKL, to expect in a diffraction pattern. So we can tell you from this structure factor that which sort of planes will take part in Bragg's diffraction. And so basically the amplitude of the resultant wave is given by a ratio of amplitudes. This F in the structure factor is basically the amplitude of the scattered wave, right? So this is basically the ratio which is the amplitude of the wave scattered by all atoms of a unit cell, and to the ratio of amplitude of the wave scattered by one electron, right? So this FHKL is basically the ratio, and as is written in here, the number of atoms per unit cell should be considered, and then these are of course electrons that re-radiate the incident beam. and when we are interested in the intensity of the diffracted wave, then this intensity is proportional to FHKL modulus whole square. So before going to discuss thoroughly the structure factors for various crystal structures, these relations should be memorized, and they will be quite useful in calculating the structure factors of various structures. So this is exponent pi I, and this is exponent 3 pi I, 5 pi I. So there is an odd integral multiple of pi I, then we will have -1. If this is even integral multiple of pi I in the exponent, then we will have a +1. So in general we can say that exponent n pi I is basically -1 to the n, and then we can get either this or this result. And exponent ix plus exponent minus iota x, this is 2 cos x. So how to calculate the structure factor for a simple cubic structure? The basic equation is written in here, and as I told you, the atomic positions or coordinates are very important for the structure factor calculations. And as you know, we have only 1 point per unit cell for a simple cubic structure, so we will choose only 1 point as our origin. And remember, we can use any other point as your origin, and you can take any point, but the most simple cases to consider, take 1 point on the origin, okay, so that we will get positions of 0, 0, 0 for u, v and w. So this FHKL is basically f of exponent 2 pi I, and this is 0h plus 0k plus 0l, and because we will have exponent of 0, and hence f, right, because we will get 1 from here. So no matter whatever we use the values of h, k and l, there are no limitations, there are no conditions for the values of h, k and l. So you can get this f result from any set of h, k, l values. So it means that for a simple cubic structure, all of the planes take part in diffraction pattern. So no matter what atom coordinates or plane indices you substitute into the structure factor equation for simple cubic crystals, the solution is always non-zero. So it means that all reflections are allowed for simple cubic structures. So these are all of the reflections are allowed in simple cubic structure. As far as the body-centered cubic structure is concerned, then for this type of structure we have 2 points per unit cell, and the atomic coordinates are, you know, the 0, 0, 0. So one of the 2 atoms can be considered as your origin. As I told you, this particularly simplifies the case once you consider 1 point as your origin. So we can say that this corner atom is the origin, okay, and this atom, this is body-centered atom, is the second atom that is considered. So this is this is half, half, half. This is 0, 0, 0. So we have 2 points per unit cell, so these 2 points are sufficient. So let's now use this equation. This is FHKL is f exponent 2 pi I, and this is 0 once you substitute all these values in the exponent, and this is plus again exponent 2 pi I, and this is h over 2 plus k over 2 plus l over 2. So by taking f common from this guy, and you will get 1 plus exponent pi I h plus k plus l. Now we can put some conditions upon h, k and l. When h plus k plus l is even, then f h k l is non-zero. Okay, so this is non-zero, and it means that we will have a reflection. And if h plus k plus l is odd, then f h k l is equal to 0, and we will get no reflection. So we will have no amplitude, no intensity, and no result, no reflection. So we can say about the conditions that all the crystallographic planes in a body-centered cubic structure for which the summation of these indices is even, then they will reflect, they will diffract, right? And if it is odd, then they wouldn't. So similarly, for face-centered cubic structure, we will choose 4 atoms because we have 4 points per unit cell, and out of these 4 atoms, 1 atom can be considered as our origin. So this is the corner atom in this structure. So the coordinates for this corner atom are 0, 0, 0, and we can choose any 3 atoms at the center of the face. You can choose anywhere. Okay, we don't have any compulsion, we don't have any limitation in choosing the atoms. So you can choose even these corner atoms, like the one in here, this corner atom, this corner atom, so anywhere in the structure. Okay, so you are absolutely free in it. So by choosing these face centered atoms, we will get these coordinates. So the structure vector, the amplitude, comes out to be, this is for the first atom, and this is for the second atom, third atom, and fourth atom. So this is the master equation. So this will be reshaped in this form, and then by taking f common out of all these terms, we will get in the parenthesis 1 plus exponent pi I h plus k plus exponent pi I h plus l plus exponent pi I k plus l. Okay, so hopefully you won't have any problem in understanding this, and then eventually this equation, right? And now we can put some of the values of HKL, and then we will find that if HK and L are unmixed, I mean all even or all odd, then f HKL is equal to 4f. Okay, so it means that this is non-zero. Okay, then what you will get, these atomic planes are allowed to reflect or diffract in a face-centered cubic structure. And as far as the mixed indices are concerned, in which for instance, you can have 2 evens and 1 odd, or 2 odds and 1 even. So this is a mixed combination, and then the final amplitude will be a null result, and then these types of atomic planes will not diffract. So these are the conditions. So similarly, we can consider sodium chloride structure, a very famous structure. Of course, this is an FCC structure, but the basis is different. This is not a simple basis. Okay, this is a molecule. So we will consider sodium, and then we will consider chlorine. And so as far as sodium is concerned, then we can choose 4 atoms. Out of them, one should be at the origin. Okay, this is 0 0 0, half half 0, half 0 half, 0 half half. And chlorine may be considered anywhere, like you can consider this chlorine. So you can have half half half. He has considered this chlorine. Okay, and then one half. So we have 1 chlorine, or even you can consider these 0 0 half. I think this is much more convenient for you to consider. Okay, you will not be confused in this set, so we can just focus on that. So this is if we consider this chlorine, okay, then the coordinates of this chlorine relative to this origin are half half half. So this is 1 chlorine, which is 0 0 half, and we have 0 half 0 and 0 0 half. Okay, so let's use these indices. For sodium, we will get the amplitude as 1 plus exponent pi I h plus k, and plus exponent pi I h plus L plus exponent pi I k plus L. Whereas for chlorine, you will eventually get this result, and then you will have FHKL is the net amplitude from sodium atoms plus the net amplitude for chlorine atoms. Okay, and then we can simplify this for f of Na plus f of Cl and exponent pi I h plus k plus L, and then 1 plus exponent pi I h plus k plus exponent pi I h plus L plus exponent pi I k plus L. So when HKL are even, then FHKL is equal to 4 f of Na plus f of Cl. So we have some primary reflections, and these reflections are allowed. So it means that all crystallographic planes in which H, K and L are even, they do diffract. And when H, K and L they are odd, then we will get 4 into f of Na minus f of Cl, and then we will get some superlattice reflections. Superlattice reflections are the reflections that happen within the primary reflections. Like if you have 2 big spots in an electron diffraction pattern, if you have 2 big spots, and within the big spots you get, suppose 1 or 2 or 3 some minor spots, then these minor spots are called superlattice reflections. These are superlattice reflections for this expression. So when HKL are mixed, then FHKL is equal to 0. So mixed crystallographic planes are not allowed to reflect. So hopefully you have got the idea of some crystal structures and then their corresponding structure factor, right? So my other video